Hello Year 10 and welcome to this lesson on half-life. So I want you to start by looking at what's happening in this diagram and see if you can describe it. Pause the video now if you need any time to do that. So what's taking place is the number of red particles in the image is halving with each transition as we move from left to right. We start out with 100. Then we have 50, then we have 25, and then we have, unfortunately because you can't have half an atom, half a particle, we then have 13. So the last box could represent 12 or 13 particles. This lesson is all about half-life. It turns out that the time it takes to go from 100 to 50 radioactive particles is the same as the time it takes to go from 50 to 25. If you take any number of radioactive isotopes and halve it, the time taken for that number of them to halve is the same, regardless of what that number was in the first place. So before attempting this chapter, you should be able to describe how radioactivity is measured, state the units of radioactivity, state what is meant by background radiation, and suggest why background radiation might make it more difficult to measure the radioactivity of a sample isotope. Pause the video now if you need time to think about these or look them up. I will give you the answers in a moment. So first of all, describe how radioactivity is measured. It is measured using a device called a Geiger counter. A Geiger counter is used to measure radioactivity. The units of radioactivity are becquerels. B-E-C-Q-U-E-R-E-L-S. Becquerels. Now these are not to be confused with a different unit called sieverts, which are the units of radiation dose. So becquerels, essentially, one becquerel is one ionizing radiation being emitted per second, whereas sieverts are the effect of those ionizing radiations on living tissue, and that works out to be 1 joule of energy transferred to 1 kilogram of flesh. So state what is meant by background radiation. Well, background radiation is the natural radiation that is around us at all times. Every object contains some number of radioactive isotopes, and so there will always be some radioactive decay going on, and so always be some ionizing radiation in the area. So suggest why background radiation might make it more difficult to measure the radioactivity of a sample of isotope. Well, let's imagine I've got an isotope which is emitting 100 becquerels, so that means 100 say alpha particles are being emitted every second. Well, if I try to measure that with a Geiger counter and my background radiation is say 10 becquerels, then the Geiger counter will read 110. So what I need to do to make sure that I measure the radioactivity of that sample correctly is, first of all, I measure the room without that radioactive sample. So I'll find that the room has a radiation of 10 becquerels. And then I'll bring the sample into the room and I'll open it up and then place the Geiger counter next to it, and then I'll find it's 110, which means that the sample was 100 becquerels. So decay is random. So radioactive decay, the emission of alpha, beta, gamma or neutrons, is a random process. This means that it is impossible to predict exactly when an unstable nucleus will decay. However, where there are enough unstable nuclei, some of them must decay in a given period of time, just due to probability. Think of it like rolling many dice at once. Some of them must show a 6, even though the number on each dice is random. The time it takes for half of the atoms in a sample to decay is known as its half-life, which is constant for a given isotope. What I mean by that is that to go from 100 to 50 is the same as going from 5,000 to 2500. It will take the same amount of time to do either of those changes. However, different isotopes have different half-life, which is determined by how stable the isotope is. The more unstable it is, the shorter the half-life. So let's go back to this idea of rolling dice. So if I take a large number of dice and I roll them, if I roll one dice, for instance, we can't predict when a 6 will turn up. But let's imagine rolling a 6 means it's radioactively decayed, and we'll remove the dice from a big box. Now in this box we've got several thousand dice. Well, in my first roll, 1/6 of them will show a 6. And so when I roll them all at once, I can remove 1/6 of them, but it's not halved yet. So I'll take that remaining number and I'll roll them all again, and 1/6 of those will roll a 6. So I'll remove those 6th. I have to do that again, and then finally again one more time before the number will halve. So if I went from 2000, it would take roughly 4 rolls of the dice before I'll get to 1000 dice. So its half-life for the dice would be 4 rolls. In your exercise books, explain why radioactive decay is referred to as random. Define the half-life of an isotope, and explain how the half-life of an isotope is determined. If you need to go back on this video and look at a previous section, please do so. So here we have a graph of the initial image we saw. At first we have 100 particles, then we have 50, then 25, and then, as I mentioned before, 13. The reason we have 13 is because we can't have a half of a decay. I mean, halving 25 should obviously be 12.5, but you can't have half an atom, so that's not going to happen. What you'll notice is that when you plot this graph, you see that each decay, when it goes from a large number to halve that number, we end up taking a single half-life. So it takes the same amount of time to go from 100 to 50 as it takes to go from 50 to 25. This is because that decay is random. But when you have a large sample of these, then we can make predictions. So I want you to sketch a quick copy of this. When I say sketch, what I mean is it doesn't need to be perfect, but you will need a ruler and a pencil to do so. You'll notice that I've added in, you notice that at the start it was 80. Okay, so there were 80 counts per second, and what I've done is I've added in a line at 40 counts per second, because that's half of 80. When you draw that line directly across to the curve and then draw the line downwards from the point where it intersects, you find that this took 2 days. So it took 2 days to go from 80 to 40. But let's look also at the difference between 40 and 20. So 20 is half of 40. So to halve from 40 to 20, it took another 2 days. So that means the half-life of this isotope is 2 days, because for the number to halve, it always takes 2 days. So I want you to add notes to your diagram to explain how half-life can be read from a graph. So that is, you take the initial count, you halve it and draw a line horizontally across until you meet the curve. Once you've met the curve, you draw a line vertically down. That will tell you the number of days it took to halve, or in fact just the time, because this might not be in days, it might be in minutes or hours or seconds or even years or millennia. Okay, I'm going to move on, so if you need to pause the video, please do so. So here we have an example of time and count rate. I want you to look at these numbers and do the following. state the half-life of this isotope, state the count rate at 90 seconds, what would it be, and state what the count rate would be, would have been 40 seconds before the first reading. Pause the video now to attempt this yourself, and then I will go through it in a moment. So this is a typical exam question where they might give you a set of numbers and ask you to work out what the half-life is. Well, if I look at 0 seconds, we've got 1000. At 10 seconds, we've got 707. That number has not yet halved. The 1000 is not halved to get to 707, so that's not a half-life. But you'll notice at 20 seconds, that 500 is half of 1000. So in fact, it took 20 seconds to halve from 1000 to 500. Now let's double check that. Let's make sure that's right. Get your calculators and do 707 divided by 2. How long will that take? Well, 707 divided by 2 is 353.5. You'll notice that that's at the 30-second mark. But since 707 is at 10 seconds, we've got 10 going to 20, that's 10 seconds, to 30, that's 10 seconds again. Similarly, we can check with 500. Half 500, what is it? It's 250. How long did it take to do that? It took 20 seconds. So there we can show that the half-life for this isotope is 20 seconds. So what would the count rate be at 90 seconds? So I've cleverly missed that one out at the end. What would it be? Well, if it takes 20 seconds in order to halve, what we can do is we can add to this table of data, we can add the 90 seconds at the far right, and we can go backwards by 20 seconds. We can go backwards by one half-life. So if we go backwards by one half-life, we find we're at 70 seconds and the count rate is 88. So what do we need to do? We must halve that number 88. And so the count rate at 90 seconds would be 44. Then state what the count rate would have been 40 seconds before the first reading. Okay, so 40 seconds is how many half-lives? Well, one half-life is 20 seconds, so that means it is 2 half-lives. That means that number has halved twice before it gets to 1000. So what's the opposite of halving something? Timesing it by 2. So we'll take 1000 and we'll times it by 2. To get 2000, and then we'll times it by 2 a second time because we have 2 half-lives, and we end up with the answer of 4000. So the initial count rate 40 seconds before this experiment began would have been 4000 becquerels. I would like you now to copy this table down and attempt the same problems. Can you find the half-life of this isotope? Can you state what the count rate at 9 minutes would be? And what would the count rate have been 1 minute before the first reading? Pause the video now to attempt this yourself, to copy it down, and I will go through the answers in a moment. In this particular case, we'll take a look at that 5000 number. Well, use your calculator to half 5000 and you'll find it's 2500. So let's have a look. How long did it take to get to 2500? It took 1, 2, 3 minutes. So therefore, the half-life of this isotope is 3 minutes. Now let's double check. I want you to take your calculator and divide 3968 by 2. What answer do you get? You get 1984. So, let's check. 1 minute, 2 minutes, 3 minutes. Yes, it took 3 minutes to go from 3968 to 1984. So again, we've shown that this is the half-life. State the count rate at 9 minutes. All right, well, it took 3 minutes, so we're going to have to go backwards by 3 minutes. So add to your table minute number 9, and we're going to go backwards. So 9, 8 is 1 minute, 7 is 2 minutes, 6 is 3 minutes. So all we need to do to find the count rate at 9 is take 1250 and divide it by 2. And that will give us an answer of 625. Yeah, 625. State what the count rate would have been 1 minute before the first reading. So we're going to put, in my own head, I'm imagining in the table, I'm putting a negative 1 minute in the top bar. So negative 1 minute, 1, 2, 3. So we take the answer at 2 minutes and we're going to multiply it by 2 to find out what it would have been. So in this case, 3,000 times 2 is 6,000, and then 3, so 6,300. So our answer is 6,300. Because if you add that to the table, you can see that 3 minutes later it has halved to 3,150. So the count rate 1 minute before the first reading was 6,300. Now let's look at how we do the same thing with a graph. Now this time it says percentage of substance remaining. Now that doesn't mean anything different, or at least in terms of a half-life graph. So you can have percentage of substance, you could have number of particles, or you could have count rate, and they will all show the same curve. So state the half-life of this isotope. All right, so what we do is we take the number 100 and we halve it. That number is 50. We draw a line directly across from 50 until it meets the curve, and then draw a line directly downwards, and we find that it took 1 minute to halve. Let's double check our answer by going from 50 to 25. So if I draw a line from 25 along until it meets the curve and then directly downwards, that happened at a total of 2 minutes, but how long was that after the 50? That was 1 minute later. So the half-life is definitely 1 minute. Estimate the percentage of substance remaining at 2.5 minutes. Okay, well in this case we just simply need to read the graph. We look halfway between 2 and 3 and we draw a vertical line directly up until it hits that curve. We then draw a horizontal line until it meets the y-axis, and doing that crudely with my finger on the screen, I can see that the answer is going to be above halfway, so I'm going to go with around 17. Yeah, about 17. But there's a little bit of leeway on this one. Okay, 3. State what the count rate would have been 2 minutes before the first reading. Okay, well, that's a slight miss question there. What I should have said was what would be the percentage of substance. Okay, but as I said, it doesn't really matter too much. So state what the percentage of substance would have been 2 minutes before. Well, if it's 100% now and it's a minute a half-life, that means 2 minutes is 2 half-lives. So 1 minute ago it would have been, or 1 minute before the start I should say, it would have been 200%, and then a minute before that it would have been 400%, because we've doubled it twice to find out what it would have been in the past. Here we have a similar question. I would like you to sketch this in your books, and well, you can print it out actually if you want to, if you can, and then attempt these questions. Pause the video now because I will be going over the answer in a moment. Okay, so let's take a look. I can see that the corrected count rate, that means the count rate after having corrected for background radiation. And we've got the time in hours at the bottom. So state the half-life of this isotope. Well, the number it seems to start at is 200. And that goes all the way down to, well, if we halve it, 100. So we take 200, we divide it by 2 to get 100. We draw a line directly across from the 100 and then draw a line directly down. You can see that the time is in fact just over 1 hour. So I would estimate by the looks of it that it is 1 hour and 10 minutes. So I think that the half-life for this isotope is roughly 1 hour 10 minutes. Let's double check that by comparing it against 100 to 50. So from 100 down to 50, well, if we move it across, we find that is, looks like just below halfway. So that looks like it's 2 hours 20 minutes. Well, that's 1 hour 10 minutes later. So it turns out the half-life here is roughly 1 hour 10 minutes. Now estimate the count rate at 3.5 hours. Okay, so we look along the bottom axis until we find 3.5, which is halfway between 3 and 4. We draw a line directly upwards from 3.5 and then draw a line directly across. Now, to my eye, that looks like it's just above 25. So I'm going to go with the corrected count rate being 27 counts per minute. And finally, state what the count rate would have been 1 hour before the first reading. Okay, well, the half-life is just over 1 hour, but this is only an hour before. So if we go back by 1 hour and 10 minutes, it would have been 400, because we need to take the number 200 and double it. Okay, so 1 hour earlier, it would have been, 1 hour and 10 minutes earlier, it would have been 400, but this isn't 1 hour 10 minutes earlier, it's 1 hour earlier. So we can estimate here. All we can really say is that it is just a bit less than 400. So I would go with something like 390. So I would say that the count rate was probably around 390. You would be able to get the marks if a question like that came up, if you said anything that was just a little less than 400. So here we have another one. I'd like you to attempt to find the half-life of this graph as well. Give that a go. And another one. Now this is a very important one to get right. So, if you think you found the half-life, then listen on. If you've not yet found it, pause the video. So in this case, we've got a trick. The graph goes up to 8,000 becquerels, but the count rate does not start at 8,000. It clearly starts at 7,500, halfway up, which means that we don't halve 8,000 to get 4,000. We must halve 7,500. That would be 3,750. So it's 3/4 of the way up from 3,000 to 4,000. That tells me that in fact it is exactly 2 seconds. Now you may have gotten that the half-life was less than 2 seconds if you accidentally halved the 8,000. So you need to be very careful. This is a common trick they play on you in exams. They will give you a graph where the numbers go above the actual starting count rate. So don't be halving the numbers that are written on the axis. Halve the number that the curve starts at. In this case, the curve starts at 7,500. So here we have a couple more tables for you to attempt. Have a look, see if you can find the half-life of these tables. And finally, if you want to work through these problems at your own pace, or you want to have some reference material, here is a textbook page that I wrote a couple of years ago.